All right, so the second set of videos is a little bit different, actually very different than what we were working on in the last part. It's kind of a mixed week here because we're going to also be starting to talk about sequences and series. The first problem says write out the sum. So this symbol right here, this weird symbol right here, this means add stuff. I know it's a very technical term, but this is the capital sigma, and we use that symbol to say add some stuff up. To write this out as a series, it tells us to start with the number 1, and then n. If there was a number like 2 up here, we'd end at the number 2, but since it says go to n, that means that we are going to have to continue this pattern forever. So the first thing we're going to do to start this out is to get our first numbers in our series. So if k is 1, we plug k equals 1, it's going to give us 1 plus 1. And then I'm going to add that to, now when k is 2, it's going to be 1, or 2 plus 1. And then we're going to work when k equals 3, it's going to be 3 plus 1. And then when k is 4, it's going to be 4 plus 1. We can see that we have a pattern forming here, right? So how do we write this sum out? Well, 1 plus 1 is 2, plus 2 plus 1 is 3, plus 3 plus 1 is 4, plus 4 plus 1 is 5. But it doesn't stop here. It goes on forever. So we use a series of dots, I use 3 of them, to indicate that there's stuff going on in here, and then we're going to use the regular formula that we have at the end, which is k plus 1. And this is how we write the sum out. Again, if I had a number n, this n was something else, let's say it was 10, I would need to write out till k is equal to 10, and then we could compute that. But since this is an infinite series that's going to continue forever, we just use the dot, dot, dot with the k plus 1 at the end. This is how we take the summation notation and write it in terms of a sum. The next one, we're just going to go right into this next video, which is express the sum using the summation notation. So now, if I am given something in this form, can I get it in that summation notation? So can I write it with that sigma? Well, I can tell you right now, one thing that we know is this series does not stop. So we know that this is going to just go to k because it doesn't have an end point. If we knew where this would end, we could find out what k would end at. Let's try to look at the pattern that's going on here. I see just the number 1 here, and that's a little confusing to me, but what I'm going to see is there a pattern in this term, and this term, and this term, and I can see this is really what's going on in this series is I'm taking 1 and I'm evaluating 3 to a certain power. So this one looks like it's 1 over 3 to the first power. 1 over 9, that looks like it's 1 over 3 to the second power. If I had the next term in the sequence, it would weigh 1 over 3 to the third power. And then all the way to the last term, which is again an infinite, but the general term here is just take 1 and raise the denominator of base of 3 to the power of k. Now what's going on with this 1 term? How can we figure out what that might be? Well, it's got to be a member of that pattern, so it has to be 1 over 3 to a certain power. And you ask yourself, how can I get a 1 down here? Well, anything to the 0 power is 1. That would give us 1 over 1, which helps us get to that original term. So what this tells us is that, I'm sorry, I got to back this up. This should say n. This is n. We're going to be taking this all the way out to n forever. But where does k start? Well, the first term is k to the 0 power. So it's the summation of from k equals 0 all the way to n, or infinity, of 1 over 3 to the k. This is how we take something that is in summation notation, like this, and get it written as a sum. It takes a little bit of work to think out this pattern, but once you get it and you figure out what the value of the exponent was where we started, we could get that side figured out, and then this ended up just being what was at the end.